Welcome, everyone. Thank you for coming today for this webinar. We're so grateful to Tom Foster from DHI to do this presentation today. Tom brings over 30 years of specialized expertise in marine and coastal engineering, particularly in the environmental impact and management of dredging, reclamation, and large-scale coastal infrastructure projects. His work has focused on sediment plume impacts, water quality, and coastal morphology, with his methodologies informing international guidelines endorsed by organizations like UPP. Since 2019, Tom has extended his sediment plume expertise to deep sea mining. He worked on the NORI-D concession in the Pacific. So in this field, he's pioneered modeling techniques to simulate long-term far-field sediment plumes from mining activities, aiming to establish environmental standards for deep-sea mining activities. Currently, he also sits on the ISA, the International Seabed Authority's Legal and Technical Commission Working Group, where he contributes to developing regulatory frameworks for sustainable deep-sea mining practices. And he developed a training course for the ISA on conducting environmental impact assessments, sharing his expertise to ensure responsible practices in deep-sea mining. So, super excited to have such an expert to carry out this webinar today. I'll let Tom take it away to introduce what he'll be talking about today.
Thank you, Becky. I hope everybody can hear me and see the screen. Spent about 30 minutes to run through the work that we did for Impossible Metals, looking at their Eureka III pilot collector test from the perspective of sediment plume modeling. This is an input to the environmental impact assessment of that pilot collector test that was submitted by BGR at the end of last year. I'll do a little bit on the background to the pilot collector test from a plume perspective, discuss a little bit of the measurement data that we received from Impossible Metals and secondary data that we received from BGR, talk about the sediment plume model development, and then present the results, including sensitivity. So, looking at the background to the pilot collector test, Impossible Metals have got an agreement with BGR to undertake a pilot collector test in the BGR concession area of the CCZ in this small little red block that you see here. So we're in the southeast end of the BGR concession. The duration of the test in terms of physical operations in the field is planned to be a total of 4 days. 2 of those days would be in what we call Mode 1 trial, where there'll be 10 tracks of length approximately 200 meters. I'll come back to the dimensions in a minute, with a vehicle speed of approximately 4.1 centimeters per second, which is expected to give a pickup efficiency of 90%. And a collection area of 4,500 square meters. The second 2 days, the Mode 2 trial, this is operating the vehicle at a faster collection speed, as you can see here, 6.15 centimeters a second. And because it's moving faster, the pickup efficiency will drop to approximately 50%. Obviously, the tracks, each track length has increased from 200 meters to 300 meters. There'll still be 10 tracks, giving a total mined area for the Mode 2 trial of 6,700. In terms of dimensions, I think the important point to recognize here is that the width of the collector is 2.25 meters, and there's approximately 16 of these collection arms devices that will do the pickup of the nodules. The bulk of the disturbance of the sediment will be close to the seabed. I'm sure you've all seen the animations that Impossible Metals have produced in terms of how these operate, but they're essentially neutrally buoyant above the seabed, approximately 50 centimeters or so. And the collection arms come down, so there's plume generated in that area between 0 and 50 centimeters seabed. And then there is some small flushing discharge higher up in the equipment. There is no discharge expected as these units return to the surface. So all the discharge, sediment discharge, will be close to the. In terms of data, we have from BGR a high resolution bathymetry, a 1 meter bathymetry that covers the test area, and that is then merged into coarser multi-beam bathymetry for the remainder of the model domain. BGR has good quality current data. The red block here is that general test area. So we have 2 instruments inside the test area, and there's various different instruments. But as we are really focused very close to the seabed here, the decision has been used to use the data sets from the single point current meter approximately 1.5 meters above the seabed. In terms of the current conditions in this particular location, I mean, there's the left rows here shows the data set over the entire monitoring campaign where we have received data from BGR, and you can see there's a slight dominant to the southeast with current speeds up to 5 centimeters a second, but generally less than 5 seconds. From a modeling perspective, given the short duration of the pilot collector test, we've elected to focus in on 2 shorter 1-month periods of current conditions. We're calling this one here in August, September as period 1, and a second representative set approximately 6 months later, January to February. The reason why we chose these 2 periods, I think you can see down here in the bottom, is that there is a clear difference in the dominant current direction between these 2 periods. Period 1 has a net southeast, but is variable in terms of direction, whereas period and is generally weaker current speeds, and period 2 has a much clearer dominant direction to the southwest, and less or slightly stronger current speeds, as you can see up here. The reason why we want 2 periods is that although Impossible Metals have plans for when their pilot collector test will be undertaken, we know from experience that plans change. So it's important from an environmental impact assessment to ensure that we bracket the possible current directions and consequently plume transport directions for the type of conditions that could be expected if there is delays to the or changes to the test program. I just move quickly through here. We have plenty of temperature and salinity data. Because we're operating so close to the seabed, essentially it can be assumed to be constant in those bottom 15 meters or so of the water column. So we've got a near bed temperature of approximately 1.48 and a near bed salinity of approximately 34.7. As you can see, there's very little variability. So that's essentially just assumed constant from a modeling. Bulk density is very important from the perspective of determining the amount of solid mass released for each, let's say, millimeter of sediment disturbed. There is good quality bulk density data, and we're seeing an average of 254 kilograms per cubic meter. This should not be confused with the what you typically see as reported densities, which are more in the order of 1400. Those densities that you often see discussed, that includes water. Of course, here we are looking at the dry bulk density rather than the wet bulk density, because it's the sediment material, and I'm using sediment in the broad sense here. It's any particulate that can be suspended. That comes from the dry bulk. Grain size, there is less information, and apologies, there's a typo here. This should say micrometers here. There's less information, and of course this is something that we would urge Impossible Metals to collect more information when they're out doing their pilot collector test. But if we compare this limited data set for the Eureka III test area to other data sets in the CCZ, it does line up fairly well. So it's not a major constraint to the modeling. One interesting difference of the Eureka III compared to some of the other collection methods, the concentrations that are developed in the near field are low. So we're not anticipating a lot of flocculation of the sediments. So settling velocities can be calculated essentially using standard formulations for settling velocities without concern about flocculation. And that's very different to some of the other types of collection systems. That means that the settling velocities will be lower. So flocculation generally increases the settling velocities, and so we are expecting due to the prevailing low concentrations near the collector, that the settling velocities will be low, and thus transport distance is relatively large for those low concentrations. The nodules are important because I think it's very easy to imagine if you think of this nodule here. The collection method essentially comes along and grabs that nodule and pulls it out of the seabed. And I have a little video later showing a lab test of that process. As that nodule is picked out of the seabed, it brings with it a small amount of sediment, particularly from underneath, but also a small disturbance of, you can see with these nodules here, there's material on the top, so that thin layer of material on the top will also be disturbed. The areas in between the nodules, essentially with the Eureka III collection method, remains largely undisturbed. So we're really interested in the surface area of the individual nodules. The AI routine in the collector will preferentially take the larger nodules, so we can divide the nodule grading, and we've therefore done that by nodule volume, nodule mass, and the assumption is made that a third of the nodules that will be collected is in this high mass domain. A third of them will be in this medium mass domain, and the collectors will always collect, so a third of them will be in the smaller nodule. And you can see the representative nodule sizes here for these three classes: 10.47 centimeters, 8.63 centimeters, 0.64 centimeters. So that's the nodule distribution that we have utilized to calculate spill rate. Turbidity. I mean, the background turbidity is only important from the perspective of establishing what constitutes a no change limit. There's various methods of calculating what constitutes no change, and when you run through the statistics given this type of variable signal from the measurements, you come to a conclusion that, provided the concentration of the incremental concentration is not above 0.01 milligrams per liter, it can't be differentiated from the background signal. And thus it's a very reasonable assumption to make that the environment will not respond to a concentration that is less than 0.01 milligrams per liter, because it's equivalent to the background signal, or it hasn't changed the background signal from what it was previously. So I mentioned at the beginning of the presentation that we took two modeling periods. I'll generally just present the results from period one. Results from period two are available in the EIA through the ISA. I mean, you can see the blue line is the current speed, varying between, let's say, 1 centimeter a second up to 4 centimeters a second, and we have directions varying between north-northwest and south during this period. Period two, stronger currents and a much more consistent. And you can see that here. So the two, the collector will obviously work slightly better if it's going up current. So for period one, we have a dominant southeasterly current. So the 20 tracks are orientated also to the southeast, and essentially what will happen is that the collector will drop in to the bottom right end of the track, and then it will move up the track here over a period of time, by which stage the hopper inside the collector will be full. It'll return to the surface with the nodules, and then come back down onto the second track and repeat 20 times. So for period one, the collector is always going from the southeast to the northwest, and for period two, the program would be swapped around, so the lines would be orientated from southwest to northeast. And you can see that here in terms of the spill. So the collection would start. We would have a constant spill. Then the collector would go back up to the surface and unload, come down, spill, back to surface, etc. And we let the model run for 7 days after the end of the program to make sure that we capture all the residual sedimentation. Picture in the video in the left, you can, I don't know how it's animating over the network here, but you should be able to see the collector coming in, going down, collecting a nodule, and as it pulls it out of the seabed, you can see that there is a little puff of sediment. In the pilot collector test, that distance that the collection system is operating is approximately a half a meter, and we anticipate that will be the area where the bulk of this sediment will come off the bottom of the nodule and off the top of the nodule. I mentioned the sizes of the nodule that we divided into 3 fractions of the nodules. You can calculate a surface area. You can calculate, depending on efficiency, how many nodules are picked per second. You know the bulk density of the material, and then the big assumption is, well, how much sediment is brought into suspension per nodule pick. And as with any pilot, I mean, one of the intentions of a pilot collector test is to verify or modify assumptions. So at this stage, this is an assumption. We're assuming that 2 millimeters of sediment on the bottom of the nodule or underneath the nodule is brought into suspension due to suction, due to local turbulence as that nodule is removed from the seabed, and 0.2 millimeters on top of the nodule. So that's where this 2.2 millimeters of sediment comes from. We understand that this is an assumption, and consequently a sensitivity test has been carried out in case we are off with this number by 100%. So we've also run models with 4.4 millimeters of material suspended per nodule. And of course, one of the measurements that will be done during the pilot collection test via measuring the concentrations in the water column close to the collector will be the verification of these of this assumption, but it is the major assumption that is made in the assessment. And with these numbers, you can work that through to a spill rate in terms of kilograms per second, dependent on efficiency, and that is what is utilized as input to the model, coming in these pulses. If we just move on to the model domain, we don't anticipate the plume to go very far. So we can have a relatively small model domain around the collection site, and you can see here the size of the domain. This orange area here in the middle is where the test will carry out. We have a 1 meter mesh inside the test area. We are, of course, interested in far-field processes here. So the material that comes into suspension leaves the immediate area around the collector and then is transported and dispersed by the prevailing current. And that mesh size gradually increases the further away from this central test area. So in the key areas, we're running with a mesh size of 1 meter, and then in the main plume area, 2 to 3 meters in terms of horizontal. And in the vertical, we're running near the bed where the plume is generated. We're running with 25 centimeter mesh, and again, higher in the water column we go, we're increasing that mesh size to have a realistic computation. We're not simulating the entire water column. The testing shows that the plume does not go above this roughly 20 or so meters above the seabed, and the bulk of it is confined to within 4 or 5 meters of the seabed. So there's no added benefit of simulating the higher parts of the water column. This just shows the bathymetry. I mean, we do have a relatively flat bathymetry here with a very, very, very slight slope towards the north. But to all intents and purposes, the seabed in this flat. The model does include density driven currents, but because of the very low concentrations, it is generated from this particular collection technology. The density driven currents are really not that important. I'll move on to presenting the results now. There's 2 types of results. There's sedimentation, so this is material that is suspended and then settles out again over the duration of the test program plus the 7 days afterwards. So this is really like an end state. And what we do here is that you'll see all of the results, and the results are plotted down to 10% of the annual background sedimentation for this part of the CCZ. So you'll see results down to a sedimentation thickness of 0.001 millimeters. Of course, this is far below what can be measured in the field. In the field, or maybe you could measure to something in the order of 0.1 millimeters, but this is a model, and the models are able to, of course, with all the limitations of the fact that it is a model, the models can resolve down to this very, very low threshold limit. And the concentrations, I'll show some animations and I'll show some statistics, and they are presented to a concentration, as I mentioned before, this statistical no change against background of 0.01 milligrams per liter. So hopefully you can see an animation here. It runs quite fast, but what you're seeing is the for period 1. Period 2. The collector is starting on the bottom left, and it's running up to the top right, and the bulk of the store strength is very close to the bed. You'll see that it looks as though there's 2 lines, and that's because approximately 25% of the spill is pushed out at the top of the collector as that material is vented from the internal hopper. The plots on the right here show the top is the sedimentation footprint, and the bottom is the bottom layer concentration. And it's obviously the production is finished here. The plume is still present. It's moving to the southwest, and you can see the concentrations are falling. We've got a couple of days of the simulation time left here. We're down to concentrations below 0.1 milligrams per liter, and this is within 25 centimeters of the bed. The plume has gone off to the southwest of the the test area. This is a sedimentation footprint. The bulk of the sedimentation, so sedimentation that's higher than 1 millimeter, you can see is confined to the actual area that is mined. Once we get out of the area that's mined, you can see some small areas here that are between 0.1 and 1. And then once we're more than 100 meters or so away, we are down to sedimentation between 0.01 and 0.1. And further away, so 500 meters away, the sedimentation is below 0.01 millimeters. So I think that gives you an overview, but let's say if we put that into context here, so this is the test area inside the BGR limit, and you can see essentially this spot here is a zoom of the red box here, and this box here is a zoom of this box here. So it's essentially that little dot that you're looking at there is the footprint, and then we're zooming in to show the area that is impacted. So if we use that 0.001 millimeters as the 10% background limit, and if the test occurs during this period 2, which has the higher, more persistent currents, we're seeing that the sedimentation footprint extend approximately 600 or 700 meters to the southwest from the area that is mined. Yeah, so just some statistics over here. 95% of the suspended sediment has deposited within 7 days. It means that 5% is still in the water column, and of course would be transported further, but at concentrations that are below that 0.01 and sedimentation that is below that 0.001. 93% of the material remains inside the mined area as sedimentation. And the plume extent is relatively small. It's less than 0.4% of the trial area that has been defined by this red block. If we look at some statistics here, obviously this is a 3D phenomena in terms of total suspended solids. It can be very difficult to visualize what's going on. But essentially what we have here moving up to the top of the slide is increasing elevation above the seabed. The layer 1 is 25 centimeters above the seabed. Layer 3 is between 0.5 and 0.75, and layer 7 is approximately 4 meters. 3 or 4 meters above the seabed, and then we have the evolution with time across to the right. So, as you would expect, the concentrations, because the bulk of the material is suspended close to the seabed, is concentrated in the bottom 2 layers. We do have that venting higher in the system, and of course there is some vertical dispersion. So there is a small amount of material that gets up into that 3-4 meters above the seabed limit. All that has settled 7 days after the end of the collection. But as I mentioned, there is 5% of the material remains 7 days after the end of the collection test, and that will continue to be transported further away, but it is very low concentration. If we look at that in terms of the vertical, as I mentioned, we do get some material up to approximately 4 meters above the seabed here. There's 1 day after the end of the collection, 7 days after the end of the collection, and then this residual plume 7 days after the end of the collection. We're down to this 0.01, 0.02 milligrams per liter within 50 centimeters of the seabed 7 days after the end of the. So as I mentioned, we did model sensitivity tests, but I mean, to all intents and purposes, because flocculation is not a major factor here, the results are linear to a large extent. So you can go back into the results for sedimentation and say, well, you know, if that assumption is wrong in terms of the amount of material that is suspended by a factor of 2, then these numbers will double. If it's off by a factor of 3, these numbers will triple. And the same for the concentrations. In simple terms, the report presents the actual model results for those sensitivity tests. But as I say, 2 millimeters is our best estimate based on the information that we have available. And then, as I mentioned, we looked at these 2 periods, and they are reported in the environmental impact assessment. The results are largely the same in terms of spatial extent, but they're just the different direction, because obviously it's the prevailing currents that are responsible for the transport direction. So just to summarize here, approximately 95% of the material that will be expended as a result of the pilot collector test will have returned to the seabed with 7 days, and 93% of the material remains in the disturbed mined area. So 7% goes outside the actually mined. Plume extent remains relatively small with respect to the trial site, approximately 0.4% by area based on sedimentation footprint. The concentrations fall to that no change threshold of 0.01, approximately 7 days post trial. And that's this 5% of the material that is remaining in suspension. And the suspended sediment concentration remains very close to the seafloor, typically within 4 meters, you know, potentially up to 5 occasionally. Obviously, the purpose of the pilot collector test is to collect data to verify assumptions, and obviously there's the whole side of the equipment performance, but the pilot collector test is aimed also at verifying the assumptions that are used to establish the sediment plume impact. We have provided recommendations to Impossible Metals on how to approach that plume monitoring to make sure, because you essentially just have one shot at getting the data. What they should do to optimize the data collection during that pilot test period from the purpose of the sediment plume. Well, one of the things that we found well is using ensemble modeling to decide where to place equipment, and then utilizing a broad array of different types of monitoring equipment to make sure that you capture the plume. It's a big ocean. It's small concentrations, so it is a skill to get that monitoring equipment into the plume, and you need a a variety of monitoring equipment to do that effectively. And then, of course, once that data is collected, you can go back and verify the assumptions in the that have been made at the present pre-collector test stage of modeling. Verify those assumptions, and then you have a high degree of confidence of scaling the analysis to a full-scale mining operation with multiple collectors working in parallel over an extended duration. So with that, I will stop talking and will happily address any questions that people may have.
Thank you so much, Tom. That was really interesting as always. And I apologize for not maybe doing an intro about the test before you started. So thank you for addressing that in your first section. But yes, for any clarity, Impossible Metals has planned to do a test with BGR in their contract area within the Clarion Clipperton Zone in early 2026. The whole cruise is scheduled in January and February of 2026. And the exact timing of when we would be throughout that cruise is yet to be determined, because they have a lot of other stuff that they're monitoring out in their contract area during that time as well. So yeah, if there's any questions, feel free to put them in the chat, or you can also raise your hand. There's a little hand button at the bottom, and that will let us know that you're that you have a question. And I see a question from Ben in the chat. So first, was current speed data gathered near the seafloor or near the surface?
So the data that we used for this particular exercise came from a single point current meter that was 1.5 meters above the seabed. There is data sets available throughout the water column, but as the plume is generated near the seabed, it is the near seabed current data set that is relevant for the modeling.
Great. So yes, it is collected near the seabed. The next one I think is probably me that will answer. Can you speak to how the Eureka III compensates for the increasing weight of collected material and maintains an optimum height above the seafloor? So that is done through our buoyancy engine system, which is as I'm not on the mechanical engineering team, but their best explanation for me is it's sort of the same way that submarines go up and down. So water goes in, water comes out. So it's the changing amount of water within a constant volume that deals with the buoyancy, and that's done as things are collected and also to rise and fall from the surface. If you would like more detail than that, I will have to refer you to our engineering team. That's what I've got on that front. And also, it's once it gets close to the seafloor, it goes into sort of a visual mode as well, sort of, and maybe a sensor like pinging the floor to sort of figure out how far it is from the seafloor. So there's some other tech that goes into that, but in terms of how it actually maintains that height, it's through the buoyancy engine. The degree and plume size, the degree of plume size and suspension seems very mild and acceptable to an outside observer like myself. Has the ISA put out any statements regarding the results of the model? No, the ISA hasn't put out any statements regarding the results of the model. In fact, we have just recently submitted, by we I mean BGR because they are the contract holder, recently submitted the environmental impact statement to the ISA, which is required 1 year in advance of the test. So that was recently submitted. You'll see some information come out soon about consultation opportunities on that document. but no, there's been no no real discussion. That may come, I think, after the test, because at this point it's very preliminary, right? As Tom said, there's assumptions that we really need to validate. So that will be done, and then I think there will be, then at that point, I think everyone will become really interested in those results and what they mean for technology for seabed mining. I hope that answers your questions, Ben. Okay, great. I think next I saw that Kieran raised his hand. So would you like to go ahead?
Thank you. Can you hear me?
We can.
Okay. Thank you, Tom. This was very fascinating modeling. You know, I appreciate it. And in particular, the due diligence which you folks have gone through, it is mind-boggling. I had one question which is related to your recommendation number 3, where you mentioned about this full-scale modeling. In there, I was wondering, as you know, the Eureka III has a boxy nature. You know, it's not a hydrodynamic shape. And when you move that boxy structure horizontally or vertically, it is going to shade its own vortices. Now, I was wondering, with this little plume which is generated in the first 5, 6, 7 centimeter, scale, as I understood, how the interaction of those large vortices from the big structure of the Eureka III or will interact with the plume and will enhance it as you go down. And in particular, when you go up, when the whole thing is full and when the entire structure is going up, there is going to be a big upset of the bottom at the ocean. All these things will be, the last question is, will all these things be included in the full scale modeling?
Yeah, I think as you progress to full scale, the near field processes, or the turbulence that you're mentioning becomes more significant. And it will, for example, help set distances between individual collectors, because what you don't want is any turbulence that's coming from the movement of the individual units starting to interact and amplify. So yes, I mean, at a full scale size, those near field processes do tend to become more significant, and I'm sure that's something that Impossible Metals will be looking at after the pilot collector test, when some of the other key assumptions are verified.
Okay, thank you very much. Yeah, thanks for the input. Yeah.
Thanks, Kieran. Kirsten noted that she can perhaps address Ben's last question about if the ISA put out any statements. I would love to hear from you, Kirsten. Hi, nice to see you.
Hi. Becky, you basically answered it all perfectly as far as I'm concerned. So, yep, well done. Then it's at this stage, as Becky said, it's not really the role of the ISA to actually comment on these modeled results or these proposals, because at this stage it's modeled, as Becky said. Once we have the results, it'll be much more interested. When you hand in an ISA, an environmental impact statement for these test models, it's not so much about the values that the ISA at this stage is concerned. It's more about addressing all the points and monitoring everything that needs to be monitored according to law. And when it comes to test mining, actually the law is not quite clear at this stage because it has not been quite developed.
Yeah, it's a really, really interesting, it's an interesting and developing space, that's for sure. Yeah. But I know that there's a lot of folks watching this to see what happens. So it'll be interesting to get the results once we're all done. Okay, there's another question here. How do the spill rates you modeled relate to the spill rate that Impossible Metals aims to apply for commercial exploitation in order to be economically viable? Are they comparable? Interesting. I might need your help to understand your question a little bit more. Does this mean sort of the sediment disturbance that would make Impossible Metals economically viable? Because I don't think that that's usually part of our, it's part of our environmental goals, but not part of our economic model. Certainly the amount of nodules we would be collecting would be part of our economic modeling. And for this test, we've done 90% and 50% so that we can see the real. During some initial conversations with a group of deep ocean scientists that we regularly consult with, they indicated that you want that to be, including Kirsten, you would want that difference to be as wide as possible. So 50 and 90 was selected, but our economic model is actually at 70% collection, so right in the middle. Interestingly, that has been adjusted over time, but that's where we're sitting right now in terms of the percentage of nodules collected. But and actually our economics come in, the model is publicly available and I can provide that link if you'd like, but our economics come in actually below published values from competition. Yeah, I do agree that a third party should be reviewing things, particularly so on the economic front. We haven't had an external audit of those economics yet because they're constantly sort of being shifted around during the development of Eureka III. So we have these sort of environmental goals that create the basis for how we want to build it. But then there's all these levers that we can pull and push in the economic model to make us more economic, like what percentage of nodules and how many arms and how many tons in the vehicle, how many surface collectors that pull the vehicles out of the water. So since we're still in that area of adjusting, we have not had it externally validated, but that is part of our plan for our next, because we're a startup company, so for our next round of funding, that's one of the things we're planning to have done. And sorry if I didn't say that, sorry if it was something else that a third party should be reviewing, let me know. I was thinking it was the economics, but maybe it's something else. And I think we have a hand up here. Go ahead, Bruce.
Yeah, hi, thanks. Hi, Tom. Thanks for the presentation. Good to hear it. At the beginning, you mentioned about the collector going through the water column. There's no sedimentation ejection from the collector as it goes to the surface. So I'm assuming there's no sedimentation sort of being washed off the nodules as they go to the surface. So it's an open collector basket that these nodules are placed in as it goes to the surface.
Closed collector basket.
Oh, okay. And when it goes to the surface, is there any washing or separating or any other washing of the nodules that would entail sedimentation that is collected or is that all retained and put in the ship?
Yeah, no, not for the pilot collector test.
Okay.
Yeah. So one of the
go ahead, Becky.
Yeah, that's actually one of our goals for the test is to see what comes up. So are we getting more sediment than we had anticipated in the hopper? Are the nodules breaking up? What is happening? So that we can improve those as we move forward. So this is very much a pilot in order to see what happens, and that will be a key goal, figuring it out, because if we get a whole bunch of sediment at the surface, that's certainly not something we want. But for a test this small, we wouldn't be sending it back down or anything like that. It would just come just come home with us. Yeah,
right. Thanks.
Yeah, you're welcome. Kirsten, please go ahead.
I'm not a physicist or a sedimentologist or anything like that. I'm just a mere biologist. How do your results, how do they compare, or where do they sit with the model that was brought out by MIT? And of course, now, you know, in this important moment, I forgot the name of the author.
Yeah, I mean, the difference, or let's say the primary difference between the work that we've done for Impossible Metals and Nori and some of the work that MIT have done is the difference in focus between near field and far field.
Mm-hmm.
And I mean, this was one of the questions early on. I mean, near field processes are important in terms of how the material is distributed into the water column before it is transported by the prevailing current. But ultimately, from an impact assessment perspective, it's that far field process that is the most important. So we are focusing for the work that we're doing, at least for the pilot collector test for Impossible Metals, on that far field process.
Would you see anything, or from that modeling that you have done so far, that your results would fit in with the turbidity wave, basically? What was his name? Gosh,
Tom Peacock.
Thank you. that they brought out.
But, and this is where the difference in technology between Impossible Metals and the let's say, for example, the collector that TMC is using, and the collector, the other collector that's been tested in the BGR area. Those collection systems that are based on suction, that they generate a bigger amount of sediment release. There's many different ways to characterize that. That's not necessarily to say it's worse, but it generates a bigger amount of sediment release. Flocculation happens, you get these density-driven flows that tend to go downslope. Because of the collection method that Eureka III is using, you're not getting that very dense sediment plume around the collector. So that density-driven effect is essentially negligible. You look at the concentrations, we're not getting above 20-30 milligrams per liter, whereas for some of the other collection systems, you're going up to hundreds of milligrams per liter, close into the collector. So they're just different. Yeah.
Yeah. Thank you so much for explaining that so well, and it was the answer I'd hoped for.
Yeah. And you know, there's various matrices you can use to compare them. So you know, you can't just say necessarily that, you know, high spill is bad or good. So you've got to be quite careful on how you present these. There's duration, there's nodules collected per kilogram of spill, etc., etc. But it results in very different transport processes. Yeah.
Okay. We're at the end of our time here, but Kieran, I want to get to your question. Is it something we could do briefly here?
Yes, I will be very brief. Tom, is this presentation open source? Because, you know,
That's
Professor Tom. Okay, I just wanted to make sure, because I interact with Professor Tom Peacock, you know, because I'm from the same school. You know, I was wondering, you know, it will be good if he sees this, you know.
Yeah.
But I have to then ask permission from Impossible Metal, you know, is it open source? Or, you know?
The presentation will, so this webinar is being recorded and it will be actually posted to YouTube. We post all of our webinars to YouTube.
Oh, wonderful. Okay, it is open source then. Thank you. Yeah. Thank you.
Great. All right. Well, thank you again, Tom, so much for your presentation today. We really appreciate it. Of course, we could take the report and try to make a presentation out of, the results, but it's never the same as getting it from the source, from the person who actually wrote it and did the work and understands the process behind it. So we really, really appreciate it. If you have any questions or you want to get a hold of Impossible Metals, I'm going to put my email in the chat. I'm the sustainability manager for Impossible Metals, and I would love to chat with you if you have any questions, comments, input, anything like that. And yes, keep an eye out because we will have consultation coming up on the environmental impact statement. So keep an eye out for that. So thank you again, everyone, and I hope you all have a great weekend coming up, whether you're at the beginning of your day, like Tom, or at the end of your day, like Kirsten.
Thank you. Thank you. Thank you.
Thanks, everyone.
Bye, everybody.